In this video we're going to take a look at the Pwn Shop challenge on HackTheBox. It's an easy Pwn challenge and the description says, we just opened a Pwn shop, time to pwn all the things. Just before I get started, note to YouTube, this is a challenge. It's on a challenge website. I'm not hacking anything. I'm trying to teach people cybersecurity techniques. I'm not encouraging any illegal activities. For some reason, YouTube over the past week have given me 2 warnings, removed videos for which I have demonstrations that I provided at university to undergrad and master's students on how to use Metasploit in one case, and in another case on a CTF that I put together, which was an Ubuntu VM, and I created a CTF where there's 3 ways to get user, 3 ways to get root, and it was just me walking through the CTF that I've actually provided to computer science and cybersecurity students before. So, and it was also private as well. It wasn't even a public video. So yeah, what you might also notice is that unless YouTube have amended this, the chapters don't work in my videos either. So since they gave me a warning, which is apparently a permanent warning on the account, and if you get 3 strikes, you're banned for life. Then since they did that, the chapters no longer work. So you might have to go down to the description to look at the timestamps if you want to skip through to different chapters. For example, skip through this rant about YouTube attacking security researchers. Anyway, rant over. Let's download these files and try to solve the challenge. So copy this over to the local directory, and let's go and do some basic file checks. Okay, so hopefully you've watched the previous Pwn challenges before this. You know how this goes. We check the file type. We see that it's 64-bit LSB executable. It's dynamically linked, so it's going to be calling out to Libc. It's stripped, so we're not going to be able to get the function names and things like that. We're not going to see where the main function, and Pi is enabled. So I think a couple of the challenges we've done so far, some of the HackTheBox Pwn challenges we've been through, have had Pi enabled. Let's run checksec here as well and just confirm what's enabled. It's running through some updates. So there's no canaries. NX is enabled, so the goal isn't going to be to inject shellcode onto the stack. The goal is likely going to be to do some ROP chains, and Pi is enabled as well. So this means that whenever the binary is loaded, it's going to load into different locations each time. So we're going to need to leak the address in order to then find offsets and things like that. So I can't remember exactly which challenges we've used this on so far. It's been a couple of weeks since I recorded, I think, the last Pwn challenge. But although these are coming out daily, they've been recorded over time. So let's run the program and see what's actually going on. We could also run strings. Forgot that. We could run strings and have a look through here, but because it's stripped, we're not going to see some of the symbols. We can get an idea what's going on with the text, but let's just go ahead and run it instead and see what the functionality is like. So we'll do chmod, make it executable. We'll run it, and we'll see here we've got 3 different options. We can buy, we can sell, we can exit. So let's check out exit first of all. You can see it just exits. Check out buy, and it says, sorry, we aren't selling right now. You can place a request, and asks us for some details. Let's put in some details. Alright, just took some details off us, didn't print anything back. Let's go to sell. What do you wish to sell? And let's just do the same. Let's see if there's some kind of buffer overflow here. How much do you want for it? Okay, and it comes back what? And it repeats some of our query, but not all of it. You can see here it's actually failed to print some of these characters. And then it says the best we can do is 1337. Let's go back and run that again, and we'll put something in here. How much do you want for it? We'll do 1337. And then they say, okay, that sounds good, leave it here so I can ask my guy to take a look. So there might be a buffer overflow here as well. It doesn't look like it, it's just our response has overflowed and gone through as answers here. Okay, let's check the buy option again. I'm going to put in a longer request here, and we got a segmentation fault in that case. We got a segmentation fault, but 2 characters that we'd entered spilled over into our command line as well. So there is a buffer overflow. There's a buffer overflow on the by, and the cell appears to be leaking something. We're not able to display this. We're going to want to have a look at this in hex and see if this is an address to something. If it is, we can go and have a look in GDB while the program's running and see what does it point to. So dynamic analysis, some basic dynamic analysis there done. We could run through it with ltrace as well, but let's open this with Ghidra and do some static analysis on the decompiled code. So we will create a new project, call it Pwn Shop, and then we can import the file. Some stuff from leak test, which was, I guess, the last video then. It's been a while. Well, it's probably not been actually that long. I can't even remember. It's just been a lot going on. Okay, so open this up. Just hit OK to all the default stuff here, and then analyze, yes, analyze, okay, and then we get into our code here. So we know that it's not going to take us to a main function. We're not going to have a main function here because it's stripped. We can see here the libc start main, but so how do we get to our functions of interest? Well, we can go through and we can just start having a look around there. You can see the first one that I happen to have clicked on has taken us to some code that we recognize, because these are some of the responses and prompts that we got. But sometimes you're going to have really big programs where there's going to be a lot of functions. Maybe there's some obfuscation and stuff done. So really a better way to do this would have been to go to the entry function and then have a look to see what's actually being called here. And we can go in and see what's being called. The first thing that's being called is this main menu. So we start at the main function. We have our options here. So we have, if it was option 1, that was the buy option. So it says, sorry, we aren't selling now. And hit here, so we have the buffer of 72, and then it's reading in 80. So there's our overflow, but that's not very much room. So although we can't inject shellcode anyway, we're not going to be able to inject much in the way of a ROP chain to that. So it's likely we'll need to pivot the stack to give ourselves some more space. So if you have seen the ROP Emporium series that I did a while ago, I believe we did some similar stuff in there with pivoting. So let's go back and have a look at the second function as well. The third function was just an exit, so let's have a look. So this is our sell function, where we were asked what we want to sell and how much we want for it. And if we put in 1337, we remember that it asked for our details, and then it's obviously going to take in the details here. Otherwise, it appeared to leak out some kind of address whenever we put in a long number of like 10 ones or something like that. So let's try and map out the variables that we have here to the code and see what's going on, and if there's any overflows or what's going on with the leaking of addresses. So if we work through this in order, we have a local 20 variable, which is, we can see here, is a pointer, and it's been assigned this data location. So this is in the .bss section, and there's nothing here, it's just all empty. It prints out what you wish to sell. It has some kind of a loop here, I'm not exactly sure what it's doing, and then it reads the input off us into this stack. So it's reading in, we can see here 1F, which is 31 in decimal, and it's being read into the stack, which is 8, but if we have a look at the type there, it's undefined, it's actually double word, so that'd be 32. And then so there's no issues there. We have 31 and then room for a null terminator as well. But then we have this section where it asks us how much we want for it, and this is where we found that if we put in like 10 ones, it was printing out some funny looking characters. So if you look here, this is being read into local 28, which is right here, and this is again 8 bytes. It's reading in 8 bytes as well, which can allow us actually to overwrite the null terminator and spill over through that variable to what's next on the stack. So if we see that if we would have put in 1337, we have another loop kind of like we had here, and then it reads in the data from us. It reads in 64 bytes, and that's being read to local 20. So that's actually that memory the pointer to this memory location. But the local 28, then, if we were to overwrite that null terminator, we can actually get into the next value on the stack, which will be this local 20, which is important because we're trying, because pi is enabled, and this is, and you can see here this address is going to load up. These are actually offsets to the address, which is going to be different every time the program loads. So we need to, whenever we run the program, we need to then find what's the base address of the program, so that we can then use these offsets to get to different ROP gadgets or whatever we need, different offsets. So let's go and play around with the application again and see if we can kind of match up the size that we had there, that 8 bytes, with this 8 bytes that are being read in. So if we go back, let me minimize this so you can see it a little better. If we go back here and run the program, we'll go straight to cell and just put in whatever, and then let's try and do 1, 2, 3, 4, 5, 6, 7. So we print that. You see we get this, the funny looking characters there. Let's do that again. We go back, cell. It's not letting me go back to cell. Okay. Well, it's not letting me do anything. Let's run that again. We'll go back to cell, and this time we'll do 8. 1, 2, 3, 4. 1, 2, 3, 4. Oh, sorry, that was the wrong thing. And again, we print out some values. Okay. If I go back, so it doesn't actually let me go back after that. Let's go back and do this again and do 6 this time. 1, 2, 3, 4, 5, 6. And in this case, it doesn't print anything out. So it's as soon as we get to 7 that it's actually printing that out. Again, we can go back and say 1, 2, 3, 4, 5, 6, 7. And you can see there it's actually printing that out on a new line. So we want to go and try and capture this. You capture this in Python or something. We'll go and set up a PwnTools script anyway and capture this and try and convert it to a memory address, and then we'll go and look in GDB and see what does that actually translate to, where's that pointed to. But what we would hope it's going to point to is the next value on the stack, which is actually this memory location. And because we know here that this memory location is at this offset, we can then subtract this offset to get to the base of our application. So we're going to go and open up GDB here, open up PwnDbg, gdb-PwnDbg, and pass in Pwn Shop. Very quickly, I'll mention, as usual, if you're in here, you can run help, get a list of commands, and you can say help aliases or something else. I don't have any aliases, like help data, and you'll get more commands. You can keep going through like that. You can also type PwnDbg, and you'll get a list of different plugins and things that you can call. So we could call radr, for example, from in here. In fact, you can just do R2, and we could do AA to analyze, AFL to look at the functions here, and then we could go and disassemble this in here. And this actually gives us a main method, even though it's detected essentially the main method, even though we don't have. And you can see we have our offsets here and stuff as well. So if we want to fill in our PwnTools script later, it's quite easy to go and grab offsets and things in here. We can do ssim. We'll do smain, not man, smain, and then PDF. If we want to disassemble, you can do Control and V, Shift and V, Control and V, or maybe you can't do it from here to skip into visual mode. You can do that from outside of GDB. Anyway, let's go back to our PwnDbg what we could do is, it's been a while since we've done it, I think, is look for an offset. Let's do cyclic 100. We're not really not going to need 100 because we know that we only had 8. Was it 8 bytes? It might have been 8. Let's find out here. We'll find out. So let's run. I've copied the cyclic pattern. We've run the program. We're going to do buy. And it says, yeah, we're not selling right now. We're going to paste in this long pattern, and it comes back and it's failed. It's got a segmentation fault like we'd expect. It doesn't have our cyclic pattern in the RIP because 64-bit won't load it, so we have to take the value out of the RSP here, and then we can do cyclic-L to look for that, and it says it must be 4 bytes. Okay. Oh, sorry, we want the first 4 bytes. What am I doing? Cyclic-L, we look for the first 4 bytes, we find it's 72 bytes in, so essentially what we knew here anyway. Let me go back. Entry, let's go into our function. We've got our, so if we hit 1, it's going to be this buy, and we know that we had 72 bytes here, and right here it's reading in 80. You can see here the 50, we highlight that, we see it's reading in 80. So it's actually, we've only got the 8 bytes available, which is going to be just enough for us to jump to somewhere in memory. So essentially what we're going to need to do there is create some more space or pivot the stack, and we'll look into that shortly. But that's our offset calculated anyway. One other thing I'll mention here is in PwnDbg, let me minimize this so you can see a bit better. We can do piebase. So whenever the program loads, although we need to actually leak the piebase because we're going to be running this against a server, so we need the value to be leaked back to us because we can't just open up GDB and do this. But locally, whenever we're testing this out, we can just run piebase, and that'll tell us this is the base of the binary. We can also do, you can search here piebase. Let me do piebase-help, and you'll see that actually if we pass in an offset, it will give us whatever offset we're looking for. So for example, if there was something in here we wanted to jump to, I could just copy the offset, and we could say, I'm missing a C there, but we could say piebase 0x 7C, and this will give us the offset of that. I think because of whatever I've picked there, it's not really given a. This is something like outside of the code. Yeah, I'm not even in the Pwn Shop function, that's why. Let me see. Let me go back. Alright, I'll do this again. This is the what you want to do. So let's copy this. The what you want to do string. If I go here and do piebase and give the offset of that. Oh, it's beyond the memory pages. Okay. Maybe it's because we've already crashed the program. Let me run this again. Let's set a. We can't break main here. Info functions. What I'll do, I'll open up ret2libc because we saw that whenever we checked the functions here, it gave us the main. So let's do that instead. Let's copy this. I'll exit that again, and we'll say what we can actually do here, rather than even doing the piebase, we can do break RVA. So let me do break at RVA help, and you'll see here break RVA. This will break at basically the offset here from the piebase. So we can pass in break RVA 0x, and that is the offset that we just found to main in ret2libc. So we can do that. The program's not being run, so it's not going to allow us to do that. So I'll exit that. We're already in the main method, so I can't do that now probably, but well, you can set the breakpoint anyway. We can do piebase as well. This would have basically done the same sort of thing if we did piebase and then 0x and that address, and that's just basically going to calculate what is the offset. So it's just if you're jumping between PwnTools and GDB, it can be handy to calculate offsets on the fly if you need to. Okay, hope that didn't cause any confusion. let's go ahead and create our PwnTools script and start automating some of this. So we'll copy the PwnTools template as usual. PwnTools template, we'll just call it exploit.py for now. Be careful calling things, I was going to call it pwn.py there, but if you're importing like the Pwn library, and you can have problems, so just be careful with the naming of things. And let's open this up, Codium, and start to make our initial changes. So just a little bit of a refresher for anybody who's watched the previous Pwn videos before this, which hopefully you have, or for anybody that's new and hasn't watched those, I recommend you go back and watch them. But if you haven't and don't know the drill here, this template, particularly if you're new to these challenges, might look a little bit daunting. Most of this is just, you just leave this as it is. We just have some functions here for starting this, depending if we want it to run remotely, if we want to debug in GDB. If we do want to debug in GDB, we can insert breakpoints and things here. We can also, if we want to, let's say, get the piebase, we could put that in there as well. Just any command that you can run in GDB, we can run here basically. We could do our break RVAs as well to set that to break and get our offset from Radar or from Ghidra, wherever. We have a find IP function here, which will find our buffer overflow. So I'm going to comment some of this out. In fact, take some of this out altogether. We're not going to be writing a payload to a file. We're going to be getting a shell. We're not going to be getting a flag. So let's change this and just say got shell, and we're going to do io.interactive. And I'll just take this out of here for now as well. We'll leave in our sample payload structure. So this is going to start the program, but before we start the program, we're actually going to send this off here to get to find out how many bytes do we need to overwrite to get our overwrite the return address. So we know that we need to go to the buy function. Let's go back here. We go to the buy function. It's 72 bytes. We're going to put in 80 bytes. So we already know this, but we can just automate this anyway. So let's first of all just update this with our binary name, Pwn Shop, and this is going to find the context for us. So it's going to create this elf object, and it's going to set the context to be used in this whole script to the properties of this elf file. So it's going to get the architecture, the bits, the operating system, and things like that. So whenever we're building our payloads, we don't need to worry about saying pack this as a 32-bit variable, as a 32-bit address or a 64-bit address, whatever. We don't need to worry about that. We don't need to worry about if we're using shellcraft and we're grabbing shellcode from there. We don't need to specify what architecture and what operating system. It will do all that for us because we're specifying it here. We can also set the log level, so debug's really handy if we're trying to identify any problems with our exploits. So I'll set that to debugs to begin with. And let's get this offset. So there's at the moment it's set up for 32-bit. I'm going to comment that out, and just because we're going to read from, rather than reading from the program counter, we're going to read from the stack pointer because it's 64-bit, and then we're going to find the offset. So we just need to update this slightly as well. Whenever we run the process, it asks us what, we can go ahead and just double check this. We run it, it says what do you want to do? We want to buy, so we're going to enter 1, and then it's going to ask us for details. So let's say here, let's copy this actually, we're going to need to send a couple of statements. So the first one, it's going to say send line, yeah, it's send line after this anyway, and we're going to send it a 1. And then it's going to ask us to enter details, so we'll say enter details, and that's when we'll send it the payload. We'll wait for the program to crash, and then we'll be able to read this from the core dump. So let's go and comment some of this out for now. And oh, that was the wrong thing to run. Let's run Python exploit, and this runs through. You can see there's quite a lot of stuff going on because of the debugging, but don't worry about that. And it's found us the 72 bytes, so it's located the RIP offset at 72 bytes. So now we want to have a look at the address that was being leaked and verify if our suspicions were correct. Let's go back once again to the right function. So we have our cell function here, and we want to go and see if we enter too many characters into this read statement, is it going to leak the next value on the stack, being this local 20, being this data location, and if we get that, can we then subtract the offset and get back to the piebase? So let's go and try and put that together now. So we start the program, we're finding the offset, this time we want to sell something. Let me go and just copy this, and after we get our initial output we want to say 2, and let's just run through this again. So let me clear that. We run it, we put in 2, it says what do you wish to sell. I'm going to copy this. You don't need to copy all of it, you could just do it after the question mark, but I kind of like sometimes just to be able to see send line after, just to be able to see, looking through the code, what's going on, you know. Not really necessary. So it's asking what do you want to sell. It probably doesn't really matter here. This was where I think it was a 32-byte variable and it took in 31, so it doesn't matter, we could say anything. And then we're going to do this again, send line after. Let's see what else it asked us. It's probably easier to do it from Ghidra just so that we don't keep getting cut out here. How much do you want for it? And this is where we want to try and put in some different values. So if we put in 6, if we remember before, we didn't get any problems. It was whenever we started to put in, whenever we put in 7, we started to see some funny looking characters. So I'm going to just send it 7 A's, and then we're going to want to receive our address. Let's try and run through this, and I'm just going to do print io.receive. Let's run through it. Python exploit, and it comes back with the A's and this question mark. Okay, I'm gonna say we'll change this. I'm gonna change this to, I'm gonna add another line here. We'll say receive until, and we want to receive until we get our A's back and that new line. So I'm going to do a new line, and then we're going to print out what we receive after that. Invalid int for literal. We're missing out until, receive until. We run that, and you see that then on our next line the first thing we get looks like our address. So we can go and have a look at another example for this. What I'll do is I'll do codium / shooting star. I remember we had some leaking on this. What do we have? Shooting star.py, and I'm just going to go here and find the leak. It's right here, so just going to grab all of this code, and we'll do a similar thing here. So instead of printing that out, we're going to say our leaked address is equal to unpack, and we're going to take in this io.receive, and we'll say that's just the leaked address, and print this out. So we'll try to run that now. Python exploit. We get our leaked address, which is good. We want to go and verify that the address is correct as well. So let's run this with GDB. If I run this with GDB, it prints out our leaked address. It's closed the connection. But we printed the piebase here somewhere, right? So it printed piebase. There we have our leaked address. And the piebase, if we have a look here, we can do Python-C. Actually, we should have got the what I'll do to make that a little bit easier, I'm going to go back, I'm going to say piebase there, and then I'm also going to say piebase, and then let's get the address of our data section. This is what we're expecting to leak, so I'm going to take this, I'm going to copy that, and we'll say piebase 0x. Let me run that again, close down that GDB terminal, clear this. Let's run it again, and we'll see, closes the connection, but that's fine because we're just looking to have a look and see, does this address match? So we've got our pi address, and you can see the second address does match. So in the first address, that was just our piebase. In our second address, we've got our piebase plus the offset to the .bss section, which we know was this pointer here. So this is important because what this means is, although we didn't leak our piebase address, we know that this address that was leaked is equal to this address plus the offset, because we've just calculated that there. So if we go back to our code and say the address that's leaked out here, we can say our piebase, let me put this on a new line, piebase address is equal to our leaked address minus what we just added on right here, so minus this value. And now if we print that as well, let us verify that this works as expected. I'm going to close that. I'll just run this without GDB. We run it, we get our leaked address, we get our, oh, I haven't updated it to print out the piebase. Piebase address, run that again, and this time we get our leaked address, which is in here, and now we've calculated our piebase. I should have run that with GDB actually, just to let you see that. I'll run it with GDB just to see that it matches up with what we see in GDB. So in GDB our piebase is this value, and the leaked value, they both match up to what we have here. So we know that we've now calculated our piebase correctly, which is great because it means from now on we can actually just jump to other locations of the program using the offsets that we find in Ghidra or in Object Dump or IDA-Pro or whatever you're using. Actually, an even better idea than what we just did would be to update our elf address. So our elf is loaded here, and normally if you load the elf and you set this up, you can just access different functions and things like that. In this case, we didn't know what the base address would be. So now that we have leaked the address, well, I mean, we could find that out in this case, but whenever we run it against the server, we're not going to be able to. So in that case, we want to update our elf with the address that the server leaks back to us, because once we know what the base address is, then we can just access our elf as normal without having to worry about pi, if that makes sense. Hopefully it does. So I'm going to set the elf.address is equal to our leaked address minus this, and then that's actually our piebase. Let me update that to piebase. And now that we've got our piebase address, we can essentially start looking for ROP gadgets. So we know, based on some of the static and dynamic analysis we've done so far, that we have a buffer overflow in the by function, but we only have 8 bytes, so we can only write one address. So we need to find a ROP gadget in the program, which is going to give us some more stack space and allow us to pivot. And once we've found that gadget, once we've got that working, we'll know how much additional space we have to work with, and then we'll have an idea what kind of ROP chain we can put together to actually get a shell or print a flag, because we know that we can't execute our own code on the stack. So even if we do a stack pivot and create a load more space, we're not just going to be able to inject shell code, we're still going to need to return to Libc and call the system function. So it's like in some of the other challenges we've done up to now, we need to also leak a libc address because we've leaked the piebase address, but we haven't got access to libc yet. But one step at a time, let's start by finding how we can create some more space on the stack and triggering this buffer overflow. So to find our gadget, let's go and have a look in ROP. You can use ROP, you can use ROP gadget. You can search for ROP gadgets inside of PwnTools as well, but sometimes it doesn't find, or it never finds all the gadgets. So I recommend doing it in ROP. You can do ROP --file Pwn Shop, and that will give all the gadgets. You can also then use some different flags. So we can do --search and say we want to search for example, pop gadgets. So we're probably going to need to, actually let's do this now. We're going to need to get the offset of the pop RDI gadget later, because we're going to want to, whenever we do finally go to return to libc and get the system function, we're going to need to pop the bin sh string into the RDI register so that we can call system on it. So let's just throw this in now. Pop RDI is equal to 0x, and this is the offset. Obviously we need to use the elf address as well, so once we've leaked the pi address, pop RDI is going to be equal to elf address plus pop RDI. But we don't need that yet, just showing there as an example. This is kind of what we're doing. We're going through, we're finding the useful gadgets, and then we'll hard code them for now into the code later on towards the end. If you stick around for the bonus content, I'll show how we can search for this sort of stuff in PwnTools and how we can automate a lot of it so we don't even need to search for gadgets. But it's better getting to know how to do it manually first, I think, anyway. Anyway, for us, we want to do a stack pivot. I'm going to do console here. If you do console, you can do help and then get a list of different commands that we've got available. You'll see that one of them is stack pivot. So I'm going to run stack pivot, and it found one gadget. Now this isn't actually the gadget which we're looking for, so let me exit out of there, and we'll do search, and I'm going to search for sub, and instead this is the gadget that we're interested in. So this is saying we're going to subtract 28 bytes from the stack pointer, and then we're going to return. So if we've only got one address that we can inject, if we inject this address as our into our stack pointer, if we overwrite the return address, it's going to execute this, which is going to set the stack pointer back 28 bytes. And if you remember, whenever we did our buffer overflow, we had, let me go back, entry, let's go into the PwnDbg function here. You'll remember that we had 72 bytes and then we had the return address. So if we write 72 bytes, we could actually write our shellcode. We could write some ROP gadgets, not shellcode because we can't execute shellcode. We could write some ROP gadgets up to 28 bytes up until the until we overwrite the return address. That probably didn't sound too good. Let me rephrase that. We could write 72 bytes of padding minus 28 bytes, because we're going to do 72 minus 28 bytes of padding, and then we're going to do 28 bytes, which are going to be our ROP gadgets and maybe some more padding, and then we will do the return address of this gadget. So essentially, whenever the buffer overflow occurs, it's going to run this gadget. It's going to jump back 28 bytes to the beginning of our ROP gadgets, and that's going to be when that's where we're going to put our ROP gadgets to leak a libc address, so then we'll be able to go and look for our system function and things like that. So it'll make a bit more sense when I start to put this together. Let me grab the offset of that, and we'll go back to the code and we'll call this sub rsp28. So if you've watched some of the previous videos, the HackTheBox Pwn challenges that I've put up walkthroughs for, I think the last one where we needed to leak the libc address, we leaked using the write function. So essentially what we want to do is we want to call a function. In this case we're going to try and call the puts function, and we want to leak the address of the puts function in the got table. So as long as puts has already been called, that means essentially that the program's already already made a call out to libc and has populated the address of that puts function in libc. Now we know that as soon as we call the buy function or the other function, the first thing it does is call puts. So we know that table is going to be populated. We don't need to worry about populating it first, which is something that I think we did have to worry about in a previous example. What we do need to do is find the address of puts. So we could just look for the puts call here and use this address offset. We're going to make life a little bit easier for ourselves, and we already did do that actually by setting the elf.address equal to this leaked address. So we actually know the PwnTools knows the address of all these different functions already, so we can kind of go ahead and just start to put it together. So before we build up our payload here, we'll build up a ROP chain. So I'm going to create a new variable here. This is going to be like a payload to go inside of our payload. So we're going to call this ROP chain. We're going to do flat. Flat will mean that everything inside this is, you can see here, it's going to take an arbitrary number of arbitrary nested lists, tuples, dictionaries. It will then find every string and number inside of those, flatten them out, etc. So basically the context that we've defined up here, it's going to, any addresses, any numbers, things that we put in there, it's going to make sure it all works properly with, in our case, a 64-bit Linux elf executable. If we're dealing with little endian addresses, it's going to know that, it's going to do all that for us, we don't need to worry about it. Because we've also done our elf address here, we don't need to worry too much about calculating addresses here. The first thing we do want to do is get our puts into the RDI. So first we got this, remember we got this pop RDI right here, so we've got the offset, and we're going to say the first thing in our ROP chain is going to be elf.address, which is our piebase that we just calculated, plus pop RDI, the offset to pop RDI, and that is going to put the next value that we place here, is going to pop that into the RDI, and that value is going to be elf.got.puts, which is going to, you can always go and print out the got table and stuff here. We could just do pprint elf.got and have a look at things if you need to. But so that's what we pop into the RDI is elf.got.puts, and then we're calling elf.plt.puts, just similar to how we've done in previous examples. And this is essentially going to call our PLT puts on, and it's going to put out the got puts address, which is going to be our foothold into the libc library. Once we have that location, then we can just remove the offset of the puts function in libc and get back to our base, and then we can then add the offset of our system. And I'm sure if you watched the previous videos, you'll have it. You kind of probably sick of hearing this by now, but just for it's important to reiterate, and for anybody who's maybe missed some of those videos, might not be too aware here. Finally, we're going to put in another address. So where do we want to return to? We're going to print out our libc puts address, but then we don't want the program to just close. We want to go back to the main menu so that we can run through again and actually send off our payload. So in here we'll say elf address plus, and then I'm going to go to Pwn Shop. I'm going to go back to, in fact, here is our function right here, 132a. So let's just do here 0x132a. So it's going to run puts, it's going to put out our got puts address, and then it's going to return to the main menu so that we can then carry on as we were. So that's cool. We've got 4 addresses here, so this is going to add up to 32 bytes. It's 4 8-byte addresses, 64-bit addresses. So it's going to add up to 32 bytes. We need to adjust our padding, obviously. So we've already calculated our offset. It was 72, and we've calculated that right here. But we can't just put 72 bytes and then our sub address, because then our ROP chain's not in there. So here we're going to say padding is equal to, and I'm going to just put in, I'm going to do offset minus the length of the ROP chain. And that means if we go and modify this, then that'll be taken into account here. And then we can just go and build up a payload. So our payload is at this offset, it's going to, I'm going to put in a dictionary. At that offset, sorry, not a dictionary, a list. At that offset, we want to, let me try and improve the format of that a little bit. Oops. Why is that deleting? I'm just trying to move it down a line. Alright, it's not. Alright, I'll just do this. This is a lot more messing about than I was planning to do right there, but it's done now. There we go. That looks good to me. Alright, so we've got our offset, and we're going to say at this offset we want you to insert our ROP chain, because the offset, sorry, not the offset, the padding, because our offset is 72. We want the padding, which is the length of our offset minus the length of this ROP chain. And we're inserting a ROP chain, and then we're inserting our sub RSP. So just like here, we need to do elf.address plus sub RSP28. So this is what's actually going to be executed. It's going to execute this. It's going to jump back 28 bytes to the beginning of our ROP chain. It's going to execute our ROP chain, which is going to put out the GOTS location, the GOTS memory address, and then it's going to jump back to the main menu so that we can go and continue again, basically. So I think that's good. Let's just to try and make this a little clearer, let's try and run through this in GDB and just see what's going on behind the scenes. I'll actually send this payload as well, so I'm just going to copy this from up here because we're doing the buy option now. Let's paste this in and change this to IO. I don't believe it's going to. Let me try and run that just quickly. Python exploit. It's waiting. So you see it's already returned to the menu there. So instead of send line after, I'm just going to send line. Okay. Just type it out by hand. Send line, send in 1, and then we're sending the payload. Let's try that. And okay, it came through. It looks like we've not actually tried to print out the leaked address or anything. But yeah, let's go and debug this and see what's happening. I'm going to go back to our code here. We have the puts. We have this read, which is where it's actually reading in our. This is where the vulnerability is. We have this read call, so I'm going to just copy that. We'll do break RVA at that location. So I'm going to do break RVA at that offset. So it's going to, once it knows what the piebase is, it's going to insert a breakpoint right there. So if we go and run this now with GDB, we can see that we've stopped at the. Did we stop at a breakpoint? Yeah, we stopped at a breakpoint here. Although it looks like things kind of carried on there. Let's see. Okay, it didn't stop properly. Let me go and enable IO interactive here. Try that again. Okay, so it stopped at the breakpoint this time as it swapped into interactive mode. Try and move this over here. So we have our breakpoint. Let's see what's happening with the instructions. So we have the call here. I'm going to do next to go to the next instruction, and you'll see that in our RSP now we have our cyclic pattern, which is the padding that's been inserted. In our instruction pointer now it's adding to the RSP 48. Let's go and have a look at the code. So it reads, you can see right here, it adds 48 to the RSP. Okay. And then the next thing that's going to happen though is it's going to sub from the RSP. So we can actually go and have a look. Let's do x over 100x. You can just do RSP $RSP. We can actually go and have a look, and we can see all of our paddings there, and we could go and have a look and see what these addresses are. This basically is going to match up to our ROP chains. So we have this sub. Let's go next then. Next we have, it's going to return. Okay. We'll go to the next. It's going to do this sub 28. So let's have a look again at our RSP. Here's our RSP right here. And if we let's actually do RSP minus 28. You can actually check there, minus 28. Let's go next instruction. So it's actually done the sub, and now we have this pop RDI in here because let's go and look at our ROP chain again. That's exactly what we're doing. We're popping GOTS puts into the RDI. So the next address on here should be that GOTS puts address. Let's go and have a look at the next address on the stack. We have, yep, GOTS puts is the next address on the stack, so that's about to be popped into the RDI. If we go ahead and do next, we can see here that the RDI oh sorry, it didn't. We didn't have the pop RDI. That was the next instruction on the stack. So pop RDI is about to occur. So we'll do next, and we'll see now that the RDI has the puts got PLT in it. And then if we have a look here, the next thing that's being called here is puts PLT. So it's calling puts PLT, and because the puts in the GOT is in the RDI, it's going to print that out. Again, we can do next, and we have then and then we're returning the elf address is going to go back to, I think I've gone into some of the puts instructions there, but yeah, that's going to go back to our main menu. So hopefully that kind of showed a bit of what's going on behind the scenes. So if we go back, we have a look here, and we'll see right enough it has printed out some address here. It looks like a libc address. We have this 7f, so we need to capture that now. So let's just go and copy the exact same thing that we have up here. We are grabbing the leaked address. So we send the payload, we grab this leaked address, and we're going to set that to, this is our GOT puts. Okay, we're going to print that. And hopefully, if we run this again, I'll run this without GDB. We run this again, and it hasn't quite printed that out. Let me strip this. Dot strip, and run that again. Okay, let me try receive line and strip it. And there we've printed out this address. So it's the we know it's the GOT puts address, but we could, if we wanted to, just to verify it, we could run GDB again. We could just hit continue and wait until it finishes. Oh, invalid address. Okay. Let's try that again. Okay, it worked that time. We got our GOTS address, it printed that out, GOT puts, and then we can do X and give it that address, and we'll see, yep, that's the puts address right there. So if we wanted to calculate offsets and stuff here as well, we could also do that. We could P system to print that's the address to system, and then we could calculate what's the the offsets from here. But we'll go and do that in our PwnTools script now. So let's go back to our exploit code here. We're leaking out the GOT puts. We need to find out then, we need to get the offset of this so we can find out the base. So I'm going to say here, we'll do libc base is equal to GOT puts minus, and then we need to find something here we need to find the offset. So we're going to print this out, libc base. And let's go find the offset now. So we can do this in a lot of different ways, but what I normally do, I'll do LDD Pwn Shop. We can see the libraries that are linked to it. We can see we've got our libc here, and we can do read elf -s, and this will give us basically all the sections. It's giving us all the addresses. We can just grep out whatever we want to find. So I'm going to grep puts, and we'll see here, here's our puts at libc. We've got this one as well, they're actually the same offset, so don't worry about it. So we'll copy this, we'll go back here and we'll say this is what we're taking away, and that's our libc base address. And then from there we want to find obviously our system address, so we'll say give us the location of system, and this is the offset of that, so copy that. Let me paste that there for a second, just copy and paste all of this, and system address is equal to our libc base plus this offset that we just found. And we can just repeat this for anything we need to find, right? So paste these in here. We need to do the same for our bin sh address, because before we call system we need to put the string, the actual string bin sh into the RDI so that it'll call, it's not just going to call system with nothing in there. Again, we can do this a couple of different ways. I'm going to do strings dash a dash tx and then pass in, need to copy this again, copy that, we run the strings, I'm gonna grep out bin slash sh slash bin slash sh, and we find that this is the offset of that string, so we'll copy that and go back to the script, we'll put that in. So this should be all of our addresses. Oh, we need to do our plus, so we're adding this, we're not subtracting it, we were just doing that to get the base address. That should be good. We could have done this other ways as well. Oh, I just closed my terminal by mistake. We could have done this some other ways as well, so let me go back to desktop, CTF, HackTheBox Pwn Shop. Remove some of these cores, and we could have run this. Let me do Python exploit GDB. We stop at our breakpoint here. We're in our breakpoint, so we could do, let me do search, just to get the help up here, search, so we can do search dash t string and then search for bin slash sh, and we could find it this way as well, so that will actually find us the address, and then we could calculate the offset from there. We could do the same again for our system and things like that, so we did p system before, and we could say piebase. Can we say piebase system? No. Okay, but yeah, we could go through and search for things and calculate things in there as well. Again, if you stick around for the end of the video, we'll actually use PwnTools to search for some of the ROP gadgets and strings and things like that, and also just load in libc as a binary directly, and so that we don't need to worry about offsets at all. We can just use the function names, and then we can just swap out the version of libc depending on whatever the server is using. So we'll move on to that later, but let me close that. I'm going to run this without GDB, and you'll see here we've got our puts, our libc, our system address, and we didn't change that one to system. Bin sh was the last one, wasn't it? Bin sh. And that will give us our various addresses. Actually, I will run that just one more time with GDB. And I'm just going to do continue. It's given us all of our addresses there. So we could go through and say, alright, this is the system address. Let's make sure it's got it right. So we can do X and then the address. We'll see, yep, it's got libc system. That's what we were looking for. We could do the same here, say X. And we'll see, alright, that's not printed it out as we'd like. So we'll do X over S. And then we'll see, yeah, that's bin sh, so we've printed it as a string instead. So just to verify that we've got everything in the right place and we've calculated all of our offsets correctly, which we have indeed done. So we can now move on to building our main payload, where we're actually going to try to spawn a shell. So I'm going to copy our ROP chain from earlier because we don't actually need to make too many changes to this. It's going to be quite a similar format. Our new ROP chain is going to, we're still going to need to pop into the RDI, but this time instead of popping in puts, we're going to be popping in our bin sh string. We're going to pop that into the RDI, and then we're going to call system. So we have our system address, and then we have so it doesn't really matter too much after this. I'm just going to leave this as the elf address. This would return to the main menu, but because we're calling system, we're not actually going to get to this. We could also just put in some padding, you know, just it doesn't really matter because we're not too worried about what's going to happen after the shell closes. If you were worried about it, you might want to just, you know, if you want to keep the server running after the shell closes, you might want to have this go back to some, you know, the main method or whatever. It shouldn't really matter for us. I'm just going to do it so that we don't need to worry about changing our padding at all. So we can just go ahead and grab this up here. We don't need to calculate our padding again, but I'm just going to put it in just in case there are any size differences. And our payload is exactly the same. We're just rebuilding our payload. It's just a new ROP chain that we're passing into it. And then we want to send this off to the binary in this case, into the server after that. So here we go. This is our final payload. Let's clear this. Let's run Python exploit. We run that. We get through, and we see here at the end it looks like we've got a shell. We don't have any end of file. If we can go through, we could go through and actually see exactly what's being sent backwards and forwards. You can see that this is so. It's no shellcode because it's the ROP gadgets, but if you have a look at these values, it'll actually be the same values as we have here. So for example, what was the last address? Or let's see, we have our system. Oh, we got an end of file while reading that. Okay, we have our system, for example, which is, or our bin sh. I can see our bin sh there. So we have our 56, so 5601 01 7f 7f 7d, obviously in reverse order. And if you go through that, it's going to be everything that we saw on the stack. So it looks like it just closed my shell there. Yeah, it did. So let me just try and run that again. And while we're here, we'll do ls, we'll do uid id, and see that we do have a shell. If there was a flag here, we'd obviously be able to cat it out. So now it's a case of testing this out against the server. If you watched the previous example where we did the return to libc, you'll know that we're going to have to go and try and find out what version of libc is running on the server, because it's unlikely that they have the same version running as we do. And if they don't, it means all these offsets are going to be calculated differently. So because we haven't loaded in libc here, we can't just go and load in different versions of libc and test it out. We actually have to go and manually update these values for each different version of libc that it could possibly be. So we'll show how to do that now. So I've just added comments throughout this code. Nothing's changed functionally, it's just been commented and maybe formatted a little bit better. And I'll put this up on GitHub. But let's go and spawn the HackTheBox server and test this remotely first of all. So just take a copy of that server address, and I'm going to do python exploit.py, and because, I mentioned this earlier, but because we have this template, anytime we want to run this remotely, all we've got to do is just pass in remote as the argument and then the server and the port, just kind of like how we did with the GDB at the beginning. And there are other things that you can pass in here as well. Notice that this is passing in debug, no ASLR. So let's run that. Let's do remote. Let's paste that in. We just need to take this colon out, and we run that. We get our end of file. So notice that it didn't actually give us a shell. We're not able to list the directories or check the ID or anything like that. So this is exactly what we expected, because we don't know what version of libc is running on the server. It's very unlikely to be the same version as ours. If it was, then that should have worked, although there can be some slight differences in sending and receiving data on the compared to the local binary to the when you're comparing the local binary to the server. some send lines might be different, might be some missing new lines or additional new lines in places, and I think we'll see that here as well. But let's go and see how we can find out what version of libc is on the server. If we take one of these addresses, this is the address that's been found on the server. Let's go to this libc database. Here you can query, so let's start over, let's remove these. We're going to add a new query, and in here we're going to put the address. You don't actually need the full address, it's only the last 3 or 4 digits which are important, but we're going to say that this is the puts call. We could have passed in a different one, oh well, we couldn't have passed in a different one. Whichever one we're leaking out, we need to find out. So we'll say this is puts, and that's the address of it, and then it'll come back and say there are 3 possible libc libraries that could be, and then it's a case of us going through and manually testing each one of these. So if we click on the first one, the AMD64, which is a safe bet for us in this case, in I can't remember which lab or which challenge we last had to do this on in the HackTheBox, but I think there was quite a few more matches that we had to run through. But you find you go through each one, starting with maybe whichever's most likely to be the case, and then essentially we'll go through and put these different offsets in there. So if we go back to our code, we have our offsets here, and you can see that in our version of libc we have to subtract this value to get back to the base, but in this version that we're looking at we have to subtract this value instead. Similarly, if we want to call system, this is going to be the offset. We can have a look at the difference there as well. So if we were comparing this to our libc, you could just take the difference, but let's paste this in here. And finally we've got the bin sh, so you can list all symbols, but obviously it's selected the most important ones for us. Paste this in as well, and if we save that and go back, let's try and run it remotely again. You see we've got end of file again, but it's as I mentioned previously, it's not just the libc library which can change. There can also be some issues with the formatting. So whenever we last ran this, let me just go back very quickly. I'm going to change those addresses back to our correct addresses, and I'm just going to run that Python exploit locally. We get our shell again. We can list the files here, but notice this difference here. Whenever we sent 51 bytes here, so we leak our piebase, and then whenever we're trying to leak our got puts, we send 51 bytes and we get back 0xA9, and it comes back with this menu. And the reason it does that is because we had this set up to return to buy after it's, oh well, both of them are set to do that, but in this case we're looking at the leaking here. So we can see that is what happened locally. It returned 0xA9 bytes. If we go to the server version, we'll find in this case it sent off 51 bytes, so it sent off 51 bytes just exactly the same. And if we look through these, it's pretty much the same, just with the correct, addresses. But instead of 0x A9 bytes, it's receiving 0x58 bytes back. So it's actually not getting the full menu back. And this is where you just kind of have to play around with the send lines and receive lines and things like that. So in this case, I believe rather than send line after, we want to change this to just send after. Let me test that out and see if that works on the server. We run that. Okay, we've still got end of file. Let's see. We still didn't get that full menu back. And so it doesn't give us that option 1. Let's try and comment that out. And if we list the directory here now, we'll see that we've got our flag.txt on the server. I'm not going to print it out because I'm conscious that I have been doing that in some videos, and I should probably just to make sure people don't just skip to get the flag. And at least, all you really have to do is run the script, so it's not too much work. So there we go. We've seen how we can do that locally and against the server. So let's do a bit of bonus content and have a look at import in the libc library and see how that can make our life a bit easier, and we'll also have a look at using ROP objects as well. So let's load in libc first of all. We load in our elf up here. I'll load it in after we start the program. We'll do libc equals elf, just like we're doing up here, and then we'll go and get our default location first of all. So we'll do ldd Pwn Shop, and let's put in the address of the libc library where we had our original offsets, and paste that in there. And where do we get our libc address here. So instead of libc base, we'll say the libc.address, just like we did with our elf.address. We'll say libc.address is equal to the got puts that we leaked minus the offset which we know about. This offset is the offset of the remote version though. Our local version was different, but we don't need to go and calculate it again. Instead, what we can do is we can say the libc address is equal to libc.symbols minus is equal to the got puts that we just got minus libc.symbols.puts, and that should get us back to our base address. And then if we want our system address, we should be able to just say, well, actually we shouldn't even need to calculate it here, we could just use it from now on, but let's try and say here libc.symbols.system, and finally we have our bin sh which we calculated the offset for. Instead, what we could do is we could say here this is equal to next, and we're going to search for we're going to do libc.search, and we're going to search for the bin/sh. We can just make sure we've got the null terminator, and this should identify everything. This should get everything as before. Let's test this out. And actually, let's test this out locally first of all. So I'm going to return this back to send line, and I will have this as well, send line after. Let's test this out and see if it works. So we run Python exploit, and we get libc base is not defined. Where do I still have libc base? Libc base. Okay, right here. So we're still printing out libc base. Instead, I'm going to print out libc address. Let's try that. And it looks like we've got a shell. Yeah, there we go. So this worked all as it did before. It's calculated the system, it's calculated libc, calculated got puts, but instead it's used our actual libc library here. So what's cool about that is that we can now go, and if we were testing this against a server, we could download all three of these libraries, and we could just test it by looping through, and just all we'd have to change in the code is we would have to update this string, and you could just create a loop to loop through. You could download every library, say there could be like 10, 20 libraries here, so you could download every library, and then you could just loop through every library until eventually you get a shell. Would be an easy way to do it. Let me download. Did I download that already? Let me download this. Actually, I will wget it to our current location. So we save that right here, and that way we can just import this. I'm going to copy that, paste it right there. And let's grab the server address here again. So we'll grab the server address, we'll run this with remote and pass in the IP import. We get an end of file error, but remember that we need to modify our code slightly, not because of this, but just because of the issues we had down here. So we want to comment this out. And we also wanted to do was it just send line or send after here? We want to do send after right there. Let me save that, test it again, and there we go, we're in. So what was cool there is our offsets didn't have to change, right? So if we coded this for our Libc library and we used all of these symbols to calculate our offsets, all we would have to do is just keep swapping around these Libc libraries to see which one actually worked against the server, rather than going and manually pasting those, and rather than having different versions of your script for each different system that you might want to test it on, you can do that all in one. So with that done, let's also see if we can make this script look a little bit better using some ROP objects. So let's start by creating the ROP object anyway. So we'll do ROP equals ROP elf, and that's going to be our context binary. You can see here what does the help say. It's a class which simplifies the generation of ROP chains, and it gives you some examples here. There's plenty more documentation on the PwnTools site anyway. So we create our ROP object. If we wanted to have a look and see some information, we could do pprint rop.gadgets. Let's try and run that. And you can see here it's printed out the gadgets. Note that it won't have all the gadgets, so look how many gadgets there are there. If I go now and do ropper -- file Pwn Shop, you're going to get a lot more gadgets. So something worth bearing in mind. From as far as I can tell from the documentation, it seems to just say that there is no way to display all the gadgets through PwnTools, and if you want to find them, you'll have to do it outside of the script. So anyway, with the ROP object created, what we can also do there is we can search for gadgets now. So rather than us manually specifying these pop RDI gadgets, we can say, oh, it's not letting me select it. We can say rop.findGadget. Actually, note some of the options we have here available as well. So you have rop.call, and rop.call will actually try to make a call to a ROP chain. So if it can find a resolvable function, you can call the function. So if system exists somewhere, for example, you could call system and pass in the arguments required here, and it will build all that together for you. And it's a really good way to learn actually, because you can do that and then you can go and do rop.dump to print out the structure of that ROP chain, and then you'll know in future, you can kind of analyze it and see, oh, that's what it's doing behind the scenes, and you'll know how to build them up in future. So it's helped me out a few times. Whenever I've struggled with things manually, I've automated them using the ROP objects, and then I've kind of analyzed what's happening behind the scenes to know how I can achieve the same thing manually. So we don't need to call anything yet anyway. Let's do rop.findGadget, and we want to pop RDI here, so we'll say pop RDI and then return. So in this case it's pop RDI and then a semicolon, then return. So we're just separating each of those inside of a list, and then that'll bring back, it'll find all the gadgets. So we want to take the first element, the first gadget that you find that's pop RDI return. We want to take that basically, and then we should be able to do the same thing here as well for the sub. So we just paste that in. We'll just change this to sub RSP 0x28, and then we're going to need to add that ret as well. Hopefully that'll find that as well. And when we get down to our first payload here as well, we have our first payload. We're creating that ROP chain. We can say here rop.raw and then pass in a list of parameters. So we can essentially just pass in this list of parameters right here. Let me take some of the comments out just for a second, just to make it easy to copy and paste. So exactly the same thing there. We've just done rop.raw instead, and then we just basically say that that's our ROP chain. So I can do, let's do chain here. We could do this at any point, but I'll just turn that into a chain now, and that's essentially what we'll send off as our payload. So we'll take this out. We're still calculating our padding, but at our padding, instead of sending this Actually, let's just send this as well, the sub RSP. Send that all as one, and then yeah, at this padding, instead of sending a list of items, a list of ROP gadgets, and addresses, we can just say here, we just put in here ROP because we've already converted it to a chain. In fact, let me take that out there. I'll take that out there and put that in there, ROP.chain. And we don't even really have to do that. We could just take this out of the payload altogether and paste it in there. Why not? Put that all as a nice one-liner. And then we can go ahead and we can do similar throughout. And let's do something similar here. We can actually probably do something even better here. I'm going to reset the ROP object. Now that we've calculated the libc address, I'm going to reset the ROP object and say ROP is equal to ROP, this time of libc. You could just create another ROP object, but we shouldn't need our first one again from now on. So there we go. We create that of libc, and then we can do ROP.system, because it's just going to look up system in libc and it's going to find it no problem, and that way it'll take care of the putting bin sh into the RDI and stuff for us as well. We can just say call ROP.system and then pass in the, in fact let's grab that, we don't need to calculate this bin sh at all. So just paste that in there. We'll take out this whole bin sh, we'll take out the system, we don't need to calculate system. We can print out the libc address because we do need to set that anyway. But that should be good. So we still need to build up our ROP chain here. I've actually just realized there's going to be an issue with our padding, because our padding here, we're calculating the offset. So I'm going to take this out of here. Yeah, okay. I'm going to take this out. We might be able to put it in there, but the padding, actually, yeah, I'm going to leave it in there. I'll leave it in there. Let's try and I'll do ROP chain here, and let me just see, we'll see how this works out. I don't think it's going to work too well, but we'll give it a go. We might need to just account for this as well. But here we go. That's adjusted the padding, and there's the ROP. I'm missing the dictionary. Okay. Everything's looking funny, so I know I'm missing another bracket. There we go. And that's looking better. Okay, so there's that. And then we've got our ROP system. We're probably going to need to, let's see if we can just add on to that ROP.raw. And then I'm going to add on this elf address to go back. I don't think we need to go back anyway, but I'm just going to add that on anyway. ROP.raw, put that inside a list even though there's only one element. And that's our ROP chain. So in this case, we'll do minus the length of ROP.chain. And then we're going to send that off as ROP.chain as well. Actually, I'll turn that into a chain here. Okay, so we have our ROP, and then right here we're going to send off our ROP, but we still want to send off our sub as well. Actually, I'm just going to put the sub in here as well because I'm not too sure if it's going to work, and it's not really a big deal to just add in. We can have in here ROP and then just having the elf address plus the sub. So hopefully this is going to work. I need to take this out of here. I'm not 100% convinced, but it might do. So let's try it. Alright, so we'll run this again. See what kind of errors we get. Okay, non-type object is non-subscriptable, so it didn't actually find our sub RSP gadget. Okay, let's see. Let's print out the gadgets again. See if it actually shows up in there. If it doesn't show up in the gadgets, it's not going to find them. So we'll do pretty print ROP.gadgets. Run that again. And do we have any subs in here? No, I don't actually see subs. So it looks like for whatever reason the subs aren't identified there. So alright, we'll just go back. For the sub, we'll just say in that case we have to manually specify the gadget. So I'll just put in what the old offset was. There's our offset, and then whenever we're doing our sub, we'll need to say, oh, we were already doing elf.address, so that would have caused some problems anyway. Oh, would it? No, that would have been okay. Alright, let's run this again. And we have that the non-type object has no attribute chain. Let's go back to the code. So here's where we're getting the chain. I'll take that out of there, and let's just say here then we'll do ROP.chain. We're going to need to do it here as well. I just want to double check. Run that again. Okay, this time we get bin sh is not defined on line 105, so I've obviously got that in somewhere still, bin sh, and oh, what were we doing here? We were still, okay, so we don't want this at all. We wanted to do just ROP.chain. So take that out. I don't know why I still had that there. I should really not do this on the fly. I should record this, but I should do this before I record the video because it's taken longer than I expected. Alright, ROP.chain here as well, and fingers crossed, and boom, we are there. We're root on the server. We've done this all with ROP objects and using the Libc library that we imported. So I hope you've enjoyed this video. If you've made it to the end, congratulations. You've got the patience of a saint. And I'll put these scripts up on GitHub along with all the others. Try to comment them throughout. And yeah, hope you've enjoyed the video. Any questions, comments, leave them down below. Thanks.